Welcome to Principles of Ecology. Today, we are going to explore one of the most fascinating and essential topics in population dynamics, the Predation Lotka-Volterra equations. We will discover exactly how mathematics can perfectly describe the endless life or death dance between predators and their prey in the wild. Let us get started. To begin, imagine a lush green meadow filled with fluffy rabbits. Because they have plenty of food and space, their population grows rapidly and abundantly. But soon, a family of hungry foxes discovers this meadow full of their favorite meal. As foxes eat rabbits, the fox population explodes. Eventually, they eat so many rabbits that the prey population crashes. Starving, the foxes die off, which finally allows the surviving rabbits to multiply again. This endless, fascinating cycle is the intuitive foundation of what we are studying today. Now that we understand the basic cycle, let us look at how it is formally defined. In ecology, this relationship is described by the Predation Lotka-Volterra equations, named after mathematicians Alfred J. Lotka and Vito Volterra. These are a pair of first-order, nonlinear differential equations. They assume the prey population grows exponentially if left alone, while predators starve without prey. By linking them through a predation term, the equations capture the continuous feedback loop where one species' success directly impacts the survival of the other. You might wonder why we need complex math to understand animals eating each other. These equations are the absolute foundation of modern population ecology. Wildlife managers use variations of these models to predict population crashes, like the famous historical cycles of the snowshoe hare and the Canada lynx. Farmers also use these concepts for biological pest control, calculating exactly how many ladybugs to release to eat aphids without using harmful chemicals. Without this mathematical baseline, human interventions could accidentally collapse entire ecosystems. Let us dive into the mathematics, starting with the prey equation. Conceptually, the prey population changes based on its natural exponential growth minus the total number eaten by predators. In this formula, dn over dt is the rate of change of the prey population over time. N is the number of prey, and R is their intrinsic growth rate. P is the number of predators, and A is the attack rate. If the attack rate or the number of predators increases, the negative term gets much larger, causing the prey population growth to slow down or even become negative. Following the prey equation, we have the predator equation, which uses a very similar logical structure. Here, dp over dt is the rate of change of the predator population over time. The term ANP is the exact same total prey eaten, just like before. We multiply this by F, the conversion efficiency, which tells us how many eaten prey are required to make one new baby predator. Finally, Q is the natural mortality rate. If the prey population drops to 0, the birth term disappears entirely, and the predators simply die off at the rate of Q. Before we move on, let us see this with a concrete example. Suppose we have a meadow with 1,000 rabbits and 50 foxes. The rabbits grow at 0.1 per month, and the fox attack rate is 0.001. We want to find the instantaneous rate of change for the rabbits. We plug these values into our prey equation. The exponential growth gives us 100 new rabbits, but the foxes hunt and eat 50. Subtracting these gives a final answer of positive 50. The rabbit population is actively growing. Now that we have calculated the prey dynamics, let us find the simultaneous change in the fox population. We use the same 50 hunted rabbits and multiply by the conversion efficiency of 0.05. This calculation results in 2.5 new fox births. However, multiplying the natural death rate of 0.2 by 50 foxes means 10 foxes are dying naturally. Subtracting 10 from 2.5 gives a final answer of -7.5. The fox population is currently shrinking because they aren't catching enough food to overcome their natural death rate. These constantly changing populations lead us to an important question. Is there a point of perfect balance in the ecosystem? Yes, this is called the equilibrium point, where neither population is growing or shrinking. The formulas for this magical point are P equals R divided by A for the predator equilibrium, and N equals Q divided by F times A for the prey equilibrium. At these exact specific numbers, the birth rates perfectly match the death rates for both species simultaneously, meaning the ecosystem is in perfect, stable harmony. Let us apply these equilibrium formulas to our previous meadow ecosystem. We want to find the exact population sizes where everything remains perfectly stable. For the foxes, we divide the rabbit growth rate of 0.1 by the attack rate of 0.001, giving exactly 100 foxes. For the rabbits, we divide the fox death rate of 0.2 by their ability to catch and convert prey, which gives 4,000. So the grand equilibrium point for this entire ecosystem is a delicate balance of exactly 4,000 rabbits and 100 foxes. Now that we have used this formula, let us understand where it comes from. We are setting out to prove the equilibrium number of predators. For a population to be perfectly stable, its rate of change must be exactly 0. We start by setting the prey differential equation to 0. By moving the predation term to the other side, we get R times N equals A times N times P. Assuming the prey population has not already gone extinct, we divide both sides by N, leaving us with the beautifully simple result that P equals R divided by A. Following the exact same logic, we will now derive the equilibrium number of prey. We set the predator rate of change to 0. This mathematically states that the birth of new predators perfectly equals their natural deaths. We move the death term to the right side. Assuming the foxes have not completely died out, we divide both sides by P. Finally, we isolate N to find that the stable number of prey is determined entirely by the predator's natural death rate, divided by their ability to catch and convert that prey into new offspring. So we have proven how the equilibrium works. But what happens when populations are not at equilibrium? Look at this graph. The horizontal axis represents time, and the vertical axis is population size. The blue curve represents the prey, and the red curve represents the predators. Notice how the prey population peaks first. As prey becomes abundant, the predator population grows, causing the red curve to rise. This drives the prey curve down, which eventually starves the predators, causing the red curve to fall. This visualizes the endless oscillating dance we discussed at the very beginning. To wrap up our lecture, let us review the most important ideas. First, predators and prey are locked in an endless, oscillating dance, where the success of one eventually leads to its own downfall by affecting the other. Second, the Lotka-Volterra equations give us a beautiful mathematical window to model this continuous feedback loop. Finally, calculating equilibrium points allows ecologists to understand the delicate balance required to prevent ecosystem collapse. You have now mastered the foundational key to unlocking advanced population ecology. Great work today.